Recording has started.
Okay, well, let's take a look at how you're doing so far. I realize some of you might not be totally done with these. For number one, we're trying to find both the area and perimeter here. For the area, this is one that might actually be easier if we fill in that corner and find the whole rectangle first, which would be 13 inches by 18 inches. What's that come out to be? 234 square inches? That it is, 234 square inches. And then from there, subtract out this missing triangle. Well, that triangle, this dimension here is 8 inches, because 8 and 5 add up to the 13. This dimension here is 6 inches, because 6 and 12 add up to the 18. Obviously, those dimensions are not drawn to scale, as you can tell. That would have to be a right angle, so we now have a 6-inch by 8-inch right triangle. So the area is 6 by 8 divided by 2, which is 24 square inches. And of course, we are subtracting there because that piece is missing. Gives us 210 square inches of area. For a perimeter, now you could have got that, by the way. You could have cut this into two smaller rectangles and a triangle and found those areas and added them up. Or even one rectangle and a trapezoid you could have used to find those areas. That's just the way that I first saw how to do it. If you did it one of the other ways and you came up with the same answer, you did it correctly. So for perimeter, we just need to pick a spot and work our way around. I'm going to start here. So we've got 12 inches plus another 13 inches there, plus 18 inches there, plus 5 inches there, plus we need this length across here. Well, that's a right triangle, so that length will be a squared plus b squared equals c squared, where a and b are those two legs, and c is that missing side. So a squared plus b squared equals c squared becomes 6 squared plus 8 squared equals c squared. So 6 squared is 36, and 8 squared is 64. Well, those add up to 100 equals c squared. So we take the square root to get that 10 equals c, or c equals 10. That corner piece was 10 inches long. That's all of our sides, so let's add those up. We got 25, 30, 40, 58 inches of perimeter. Any questions there?
Recording is on.
Okay, so number 2, finding the area. This one looks difficult, but it's not, at least for the area. For area, remember we saw in some of our other examples in the last week that you can cut them apart and piece them back together. Here's a classic example of that. I can cut this half circle off of this end over here. And that piece that I cut off is now the perfect size. Come on. I want you to let me move you. There we go. Perfect size to fit in and fill in that missing piece on the other end. So the area of this is nothing more than just a rectangle that is 20 by, this dimension from here to here is 4 feet. The difference between the 20 and 24. So across here is 8 feet. So that area is just a rectangle that is 20 feet by 8 feet, or 160 square feet of area. The perimeter is a little bit trickier. For the perimeter, we have the two straight 20-foot pieces. And then we can take these two pieces, this section here and here, and we can flip one of them over and put them together to just get one circle with a diameter of 8 feet. That'll be pi times 8, which is 25.12 feet. That'll be 25.12 feet there, which adds up to a total of 65.12 feet of perimeter. So you can see, you can go ahead and dive into these shapes brute force if you want to. But there are a lot of things we can do to cut them apart and put them back together, to piece them together, to make them simpler to find those areas. So what I want to do today is I want to take some time to have you guys try some examples of these areas, finding them in your notes, and we'll go over them. So the next example I'm going to give you is going to look something like this. Assume all those corners that are close to square corners are square corners. So let's call this piece here, I'll put it on the end. Let's call that piece 20 inches. This big piece out here we'll call 25 inches. This piece over here we'll call 11 inches. Actually, let's go the other direction. Sorry, let me do 8 inches on that. Obviously not drawing the scale again. This little piece inside here will be 5 inches. And this piece outside here is going to be 20 inches again. So area and perimeter. And I will outline the actual shape here in another color so you can see the brown is the actual shape we're finding. So you can separate it from the dimensions. Find the area and perimeter of that whole shape for me. We'll go over it in a couple minutes. find the area of this one, there's a lot of different ways it could be cut up. But typically, I try to cut them up into as few pieces as I can. So this one, I would actually just cut it like this. Cut off that half circle. Cut off this trapezoid. And I have 3 pieces. A rectangle, a trapezoid, and a half circle. So for area, piece number 1 is that rectangle that is 20 inches in this direction. Now this from here to here is 5 inches, the difference between the 20 and the 25. So that makes this diameter here 10 inches. This makes the radius 5 inches. So that'll be 20 by 10 for that first rectangle is 200 square inches. For the trapezoid, this distance across here is 12 inches, because that's just the 20 minus 8. We have 5 inches here. This is 10 inches, so the difference makes this also 10 inches. So that is a trapezoid with bases of 5 and 10. So 5 plus 10 divided by 2 times a height of 12, which is 90 square inches of area. And our third piece is that circle that has a radius of 5, but it's only a half circle. So pi times 5 squared divided by 2 is 39.25 square inches. So that all adds up to be 329.25 square inches of area. For perimeter, we'll pick a spot and start moving around. So we'll start here. We've got 25 inches plus 20 inches. We've got to find that slant across there. So to do that, we're going to cut off this right triangle. This is 12 inches here. If this whole piece was 10 and this piece is 5, well, this remaining piece also has to be 5 inches. So that's going to be 5 squared plus 12 squared equals, I'll call that x squared. At this point, I'm going to trust that you guys can work out that formula. X comes out to be 13 inches. So plus 13 more inches. Then we got 5 inches here. 8 inches there.
Wouldn't that be 17 inches?
Nope.
Because you're adding 5 and 12, that makes 17.
5 squared plus 12 squared equals x squared. So 5 squared is 25. 12 squared is 144. We add those together, we get 169. That equals x squared. Now we have to square root both of those. The square root of 169 is 13. You're not just adding the numbers together. You've got to square them, add them together, and then square root. Now we still have that half circle there. So the circumference of a full circle is pi times diameter. So pi times 10 is the diameter. But it's only a half circle, so we divide by 2. So it ends up giving us, 15.7 inches. So if we add those all up, 20, 40, 65, 78, 86, 86.7 inches is our perimeter. How many of you had that? Just give me a wave if you had it. Anybody have any questions on how we got to those answers? So what we have here, this is a square with each of the sides equal to 16 inches. And of course, each side of that square has a half circle mounted to it. Again, in your notes, try to find the area and perimeter of those for me. We'll go over them here in just a little bit. So the area for this one, actually area and perimeter, are not that difficult if you can figure out how to divide it up correctly. Or divide it up in an easy way. There are several correct ways to divide it up, but the easiest way to divide this up would be to cut that square out of the inside. That's just going to be 16 inches by 16 inches. And then take each of the half circles, pair them together. If I put those two together, I've got a full circle with an area of 16 inches. If I put these two together, I have another full circle with a diameter of 16 inches. So my area here becomes a rectangle, 16 inches by 16 inches, which is 256 inches squared. And then pi times 8 squared. If it's a diameter of 16, it's a radius of 8, which is 200.96 square inches. And there's a second one of those. This one's also going to have a radius of 8 inches. So that's going to be 657.92 square inches of area. For perimeter, well, the square part of this doesn't contribute anything to the perimeter because none of those sides are on the outside of the shape. All that's on the outside of the shape are these arcs of the half circles. Again, I could put those together to make two complete circles. So for my perimeter, I need the circumference of one of those circles is pi times 16, which is just 50.24 inches. And there's two of them. Giving us 100.48 inches of perimeter. So again, you can see if you can cut things apart and put them back together in a useful way, you can save yourself a lot of work. Like I said, there's a lot of ways you could have approached that problem. And many of them would have given you the correct answer. But that is probably the simplest way to me to break that one down. Oh, let's see here. Do this one. Okay, so we've got half circles on each end of this. This piece here I'm going to call 7 inches. This piece is going to be 15 inches. I will make this piece here 5 inches. I'm going to tell you that the distance across here is 4 inches. And let's see what I want to do here. We have 35 inches across here. Find area and perimeter again. I'll give you a little bit more time for this one. This one's actually a little more complex. Let's take a peek here for the area. I'm just going to slice it straight up and down like this. So we do have 5 sections. Section number 1 there is a rectangle that's 7 inches by 4 inches, or 28 square inches. Section 2, well, we have to figure out what this dimension is here. That'll be the same as this one here. We have 2 inches here. If that's 4 inches across, that means the diameter is 4 and the radius would be 2. So we've got 2, 9, 24, 29 from here to here. Does that look right? Yep. So that makes this 6 inches across from here. So if that's 6 inches there, that makes this 12 inches here. So that being 12 inches means that that piece there is a trapezoid with bases of 4 and 12 and a height of 15. So that's 120 square inches of area. 4 plus 12 is 16, divided by 2 is 8. 8 times 15 is 120. My third shape, this one here, that's just a 5-inch by 12-inch rectangle, giving me 60 square inches. And now we have to go back and do the half circles. We'll do this one here next is piece 4. That's just a half circle that is pi times 2 squared divided by 2. 6.28 square inches. And piece 5 over here, that is a half circle, pi times 6 squared divided by 2. Comes out to be 56.52 square inches. We add those all up. Oh, what do we have there? I get 270.80 square inches is my area. For perimeter, this one's going to have a lot of pieces. So let's just start right here. We've got 5 inches plus 15 inches plus 7 inches. Now we've got this half circle there that I'll figure out. That's going to be pi times 4 divided by 2. That is 6.28 inches. Plus, this next piece here is 7 inches. Plus this piece here. To find that, I'm going to have to make this a right triangle here. This is 15 inches. This over here is 8 inches, the difference between the 4 and the 12. That ends up being 8 squared plus 15 squared equals c squared. If you guys do that formula out, which I trust that you can do, 8 squared is 64, 15 squared is 225, adds up to 289. The square root of that is 17 inches. Plus, this is 5 inches. Plus, we have another half circle. That one's going to be pi times 12 divided by 2, because that diameter was 12. Give us 18.84 inches. So we add those all up. We have, oh geez, right here. 81.12 inches of perimeter. Any questions? Okay. Well, I'm going to have you do a little bit of homework here for a while, then we'll come back after break and we'll look at the next piece. In that packet, that one that was mounted, I believe, for September, or posted for September 23rd or 24th last week, it's pages 174 through 177, dealing with area and perimeter of composite figures. So do those problems that are in the gray boxes. So we will give you the last 13 minutes here, 13 and a half minutes of the first hour here to work on that. Then we'll take a break. Then we'll come back and we'll work on our second hour of class. about that time. So if you want to take a break, we'll come back and we'll start lecturing at about 1:30. about that time, so let's go ahead and get rolling here again. So, what we want to talk about for our second hour here is a shape that actually comes up in construction more than you would think. Come on. There we go. And that is an octagon. Now, an octagon, hopes if I spell it correctly, is just a shape with 8 sides. What we're more concerned about is a regular octagon. In a regular octagon, all sides are equal, and all the angles are equal. Because in a regular octagon, it makes it just way simpler to find each of those dimensions when we're looking for them. So let's start out by looking at some of the features of our octagon that we're going to be using. So pretend that looks like a regular octagon. One of the features we have is the length of the side. We're going to call that S. So if we know the side, the area of that octagon is equal to 4.8275 times S squared. What does that mean? Well, that means if we have an octagon, whether we're looking at a gazebo or whatever, let's say it has 6 feet of length on each side. That area is 4.8275 times 6 feet squared. Giving us 173.79 square feet of area for that octagon. Well, another dimension that we have is called the flat dimension. The flat dimension goes from one side to the opposite side, perpendicular to both sides. It's measuring the distance across the flat way of those two sides. If I know that flat dimension, the area is 0.8284 times that flat dimension squared. So if I have a regular octagon, and I know that flat dimension, I can draw it out here, is 16 feet. That area is 0.8284 times 16 squared. Now you think about this, it makes sense. 16 squared would be this whole square out here. So we're missing those little corners, so the octagon's slightly smaller than that. That 0.8284 makes sense. 0.8284 times 16 squared. 212.07 square feet of area for that octagon. The third dimension we're going to look at is called the diagonal dimension, D. It goes corner to corner across the octagon instead of from flat side to flat side. So if I know the diagonal, the area is get back here. 0.7071 times that diagonal dimension squared. So again, pretend that looks like a regular octagon. If I know that the distance across this octagon is 20 feet, that area is going to be 0.7071 squared. Here's 282.84 square feet of area. These dimensions, they said these octagons in whole or pieces pop up way more than what you would think in construction. Whether it's an octagon-shaped gazebo that somebody wants built out in a yard or off the corner of a deck, or a room, a turret-type room sticking off the corner of the house, generally are built as octagons rather than truly round. We can look at, let's say we have a space restriction. Let's say we need to fit in a maximum area of 500 square feet. For building code, some areas have limits on outbuildings. If they're more than a certain size, they have to be counted as an outbuilding rather than just an ornamental. Like for garden sheds, it's usually 100 square feet. That's why so many garden sheds are 8 by 12, because that comes out to 96 square feet. It's less than 100 square feet. So our max area of 500 square feet, let's say I want to know what is the side length. What will S be? Well, I know that the area based on the side length, 4.8275 times the length of that side squared. So if I have an area of 500 square feet, find what side length we would have, we're going to have to work backwards. If we knew the side length, we would square it and then multiply by 4.8275. Go backwards, we're going to divide by the 4.8275. $500 divided by 4.8275. And then we're going to square root that result. That was what, about 103.6. That's my side squared. So to square root that, note what I'm going to do is I'm going to leave it in the calculator. I'm not going to write it down and type it back in. I'm going to do square root, and then I'm going to do second ANS. That's telling the calculator to use that previous answer. If I were going to write it down and type it back in, I'd want to keep it to 3 or 4 decimal places rather than just the one that I wrote down. But using the ANS key allows me to have the calculator use the exact answer that it had from before. So 10.18 feet is the length of the side. So that would be the maximum length that I could have for the side of an octagon if I had to stay under 500 square feet. So let's say we have a customer that wants an octagon with a side that is 10 feet. We want to know the length of the joists. They're going to be required to go across that the long way. So we know this is 10 feet. We want to know how long these joists are going to have to be that go across at the longest dimension like that. So that's what we're trying to find. Well, we can actually use this to work forward and then backward. Forward, let's do area based off of that side. 4.8275 times that side length, which is 10 squared. That gives us 482.75 square feet of area. Now that we know the area, we can work backwards to find the length of that joist, which is the flat dimension. The area based on the flat dimension is 0.8284 times that flat dimension. Well, since we know that the area is 482.75, we calculated that from the length of the side, we can now work backwards to find that flat dimension. So we're going to divide by 0.8284. You get 582.75 equals our flat dimension squared. Now we got to square root it. 24.14 feet. So we know that's 24.14 feet. The question is can I get away with a 24-foot joist, or do I have to go to a 26-footer and cut it down? Well, when we do our framing, we know there's going to be some sort of a rim joist on each end. So if this is less than 24 feet 3 inches, we can get away with it. The rim joist will probably be 1.5 inches thick. So that would be a total of 3 inches. So let's convert this to feet, inches, and sixteenths like we did on a worksheet earlier. We are going to take our 24 feet. We're just going to keep that. We're going to take the 0.14 feet, and we have to convert that to inches. That's going to be times 12. Which is 1.68 inches. Which is well short of 3 inches. So we know there's going to be 1 whole inch here. Let's just do that. Let's bring down my 1 whole inch. Let's take the 0.68 and convert it into sixteenths. So 0.68 over 1 times 16 over 16. 0.68. So what I'm going to do here is I'm just going to subtract 1 and then take the 0.68 times 16. Gives me 10.88. That's between 10 and 11. Well, 10.8 is way closer to 11 than it is to 10. So that is 24 feet, 1 and 11/16 inches. So we know the 24-foot joist will work. We're actually going to end up cutting off about 1 5/16 from that 24-foot joist so that we got room for the rim joist. Let's say I want to find the longest side that we can have on a gazebo that will fit on a 24-foot diameter circular pad. I've had this happen to me before. People take down corn cribs or other structures that are round, and they have this concrete footing there. They want to build something on it. What's the largest gazebo? What's the largest side we can have on a gazebo that will fit on a 24-foot circular concrete pad? So that means we have this 24-foot circle. It's going to fit like this. So that 24-foot diameter is the diagonal length, D. So let's find the area of an octagon that has that diagonal length of D. That area is 0.7071 times D, which is 24 feet here. 24 squared. giving us 407.29 square feet of area. So if I want to find the side, I know my area is 407, not 402. Is 407.29. And the formula for the area from the sides is 4.8275 times that side length squared. So the first thing I have to do here is I have to divide by the 4.8275. So I'm going to do that. 407.2896 here, divided by 4.8275. 84.37. That's my side length squared, and then I'm going to square root it. So the square root, second square root of that answer, I get 9.19, probably 9.18 feet for the side length. If I rounded that up to 9.19, it would probably hang over the edges just slightly. So I have to keep it on that circular piece. So here I'm not so worried about the mathematical rounding. I'm worried about the situation saying I'd rather be too small than too large, so I round it down. Any questions on those? So let's look at a slightly more complex example. Let's look at a half octagon, or an octagon shape, but we're only going to use half of it. It comes off the side of a house like this. It's not actually even just half of it. We're cut off at these corners here. This piece is what's missing. What we know about it is each of these sides is 8 feet long. I want to find the area of that piece. Well, there's a couple ways we could go about it. What I'm going to do is I'm going to find the area of the full octagon first. That full octagon would be an area of 4.8275 times that side length 8 squared. Figure that out. 4.8275 times 8 squared. 308.96. Got 308.96 square feet of area for that whole thing. But now I need to subtract out this part over here that's missing. Well, this part is a trapezoid. I know that the trapezoid is 8 feet here, but I do not know the other base or the height. Well, let's work on those. If I actually knew the flat dimension, the base is the flat dimension. And from that flat dimension, I could find that height as well. If I knew that dimension, we could work this out. So let's work backwards from that area. 308.96 square feet equals, for the flat dimension, we use 0.8284 times that flat dimension squared. So to get back to the area, we're going to divide by 0.8284. Giving us 372.96 equals that flat dimension squared. And then we're going to square root it. So the square root, get back here. Square root of that dimension. 19.31 is our flat dimension. So what that means is on this trapezoid, 19.31, I'm going to redraw it down here. We know this is 8 feet because that's the side. We know this is 19.31 feet because that's the flat dimension. We still need this height. Well, if I look back at my original octagon here, that flat dimension runs this way as well. If I were cut here as well, this piece would be 8 feet. So these two heights here and here have to be half of the difference between that 8 feet and our flat dimension. So if I take my 19.31 and subtract 8 feet, I get 11.31 feet. If I divide that by 2, that gives me my height, giving me 5.655, I believe. It's 5.655 feet. So 5.655 feet is that dimension. So my area for that piece is the average of the base, 8 plus 19.31 divided by 2 over 2 times the height, 5.655. So let's calculate that. So I have to do parentheses around the 8 plus 19.31 divided by 2. That's the average of my base is 13.655. Times that height, the 5.655, gives me 77.22 square feet is that area of that missing trapezoid here. So I have to subtract that out from the area of the full octagon to get the area of the piece that we're interested in. That's this piece out here. Didn't that color in the way I hoped it would. This piece out here. So what is that? 74. 231.74 square feet is the area of that. Well, you might be wondering, well, why on earth would I need to know the area of that? Well, if you're doing a materials list, you need to know areas. But also, many of your home estimates and bids are done by square footage. So you have to have the floor square footage in order to use that to create your estimates for a house. With that, in that packet, page 170 uses those octagon formulas. The octagon formulas are also on that page up above, if you like. So that's all of our new material for today. So we're going to be moving on from this packet. Actually, for you guys, you'll stay in this packet. There's some stuff on the framing square that we'll look at tomorrow, and a couple other little things that we'll deal with. And then we'll move on from there. So you will still be using this packet a little bit tomorrow, but we'll also use your little book as well tomorrow for assignments. So I will give you guys the last 23 minutes here to start on homework, since I only gave you a few minutes in the first hour. I will stay on the